So the crust. The crust is the outermost rocky layer of the planet. I do stress rocky because, some people would say, well, the atmosphere is the outermost layer of our planet. Sure, if you're looking at the atmosphere, but we're looking at geology, so we're looking at the outermost rocky layer of the planet, and that's the crust. 30% of the crust is continental, and 70% is oceanic. It kind of makes sense because we've all heard that 70% of the Earth's surface is covered in water. It's the oceans. They are on oceanic crust. Now, a cool thing that we're going to look at is called a hypsometric curve. This is looking at what percentage of the Earth's surface is at different elevations. Now, the highest point is in the Himalayas. It's just over 8.5 kilometers. And the lowest point is in the Marianas Trench, just over 11 kilometers down, relative to sea level. So this is, we always talk about elevation or depth as relative to sea level when we're talking on a macro scale like this. So this is what a hypsometric curve looks like for the Earth. For some other planet it would look different, but we've got our highest point up in the Himalaya mountains, K2 and Mount Everest, ultra tiny percentage of the Earth's surface as a whole, but they are our highest point and they show up. And then as we move along the curve, you notice dropping down below 5 kilometers and we're still at less than 1%. Moving along further, we go to the right. It's cumulative percentage, adding it all up, and this dashed line in the middle is sea level. So we can see it crosses the dashed line right at 30 because 30% is continental and the rest is under the ocean, the oceanic crust. Now there is this section in the middle referred to as stretched continental crust, where you've got the continental shelf and the continental slope and then the continental rise. This is as you move off the continent, it's under the ocean, but it's composed largely of rock and sediment from the continent, underlain by oceanic crust. And then we move further and further along our hypsometric curve. We're going through the continental rise and the abyssal plains, which are even deeper. And then right at the end, right as we go from the 99% to the 100%, we hit our last few deep trenches with the very bottom point being in the Marianas Trench, 11 kilometers under sea level. So you can see only a tiny bit is very deep and only a tiny bit is very tall. A good chunk is slightly above sea level and a very large chunk is a little ways below sea level. So this is one way to look at it. Another way is taking it in a kind of almost like a bar chart, but not bars, it's just connecting them. And we see, just like I was saying, a tiny bit is super tall, a whole bunch is a little above sea level, a really large amount is a little bit below sea level, and then a tiny bit is super deep. And this one doesn't quite finish, but it will come down off the bottom of the chart to hit the 11 kilometers depth. Earth has this 2-point system if you graph it like this. We can do the same kind of graph for some other rocky planets in our solar system. They look really different from Earth. Mars is a little bit spiky, but really centered around that average sea level, even though they don't have seas, so we call it a geodetic surface. but it's basically what sea level would be. If we look at the moon, it's actually centered a little bit below the average, which, well, I should say it's not centered below the average. That's impossible. The average is the average. I should say the peak for the largest quantity of land at a given height or a given elevation is below the average. So there are quite a few land masses or land areas that are deep like that, and then lots of land at varying elevations that's higher, so it still averages out to that mean, that average. Venus, on the other hand, center peak is exactly on the mean. So the question that I pose, I know I can't call on you to, give your guesses, but you can think about it. Think about this for a moment. Why do these other planets, counting the moon as a planet here, because it's a planetoid, it's about similar in size to Pluto and Venus, or Pluto and Mercury. Why are they really centered along their average? Why don't they have this peak above and this peak below their sea level, so to speak, their average land elevation? What makes Earth have this weird double spike where the others have a single spike? So if you think about that for a little bit, I'll come back to it. I want to show you a cross-section of the Earth's crust in a kind of generic sense that shows a little bit of everything that can go on. We can have mountains, so they're tall, and they have a deep crust, often called the root of a mountain. So the crust is thicker where there's a mountain range, not just because it sticks up, but also it sticks down. It actually sticks down more than it sticks up. Then we have the continental platform. This is where most of the continent is at this elevation. It's the non-mountains. And the crust is reasonably thick, but not as thick. Then we have the continental shelf. This is the shallow coastline. This is off the east coast of the United States. It is not like the west coast of the United States. That's a different scenario. But, we've got crust and it's covered with sediments and stuff, and then covered in ocean water. The continental rise, where it goes from this shelf down to the true ocean floor, which is called the abyssal plain. This is the large expanse of deep ocean floor. Then we get to a mid-ocean ridge, and this is a hill-like structure that's very long. There's magma coming up and solidifying into rock. We see one down the center of the Atlantic Ocean. We see them in many, many different places around the world. We can see little things like seamounts, underwater mountains, basically. Then we move along, and on the far side of the ocean here we have a trench and this weird fan-shaped thing, which we'll talk about shortly. And then we move up onto a continent with a volcanic arc. So we've got volcanoes going on. This is kind of like the west coast of the United States. We've got, this is also like Japan or the Aleutian Islands up in Alaska. This is a place where we've got subduction going on and we've got volcanoes happening. So, west coast of South America, very precisely like this. West coast of the United States, not so much anymore. the ocean crust itself, this is a really pixely image, I know, but if you like retro video games, this will make, you'd be like, oh, I can see everything you're talking about. So anyways, at the top, we've got the seafloor. Above it is water. And so the seafloor is all sediment. It's fine silt and limestone goo and stuff. It's just nice sediment. Then we get into pillow basalts. Pillow basalts are created when lava is just coming out, like at a mid-ocean ridge, and cooling very quickly and hardening and lumps and piles on top of the old lumps and piles, and almost looks like pillows. Below that pillow basalt are sheeted dikes. These are vertical or really close to vertical, flat, so extending side to side, dikes coming from down below and cutting up into the pillow basalts. Below that is gabbro, and below that regular gabbro is cumulate. Cumulate is also gabbro, but it's special gabbro. It's gabbro that's even more iron rich. It's the stuff that crystallized very first as a magma chamber was solidifying, and it was so iron rich that it crystallized first and was denser and settled to the bottom before the whole chamber finally got too far along the solidification process for anything to settle, and then finally completely solidified. At the bottom of that cumulate is the moho. Again, you've probably heard the term. I'll talk about it a little more shortly. And then below that we hit the mantle, because below the crust is the mantle. Now, I know I've been talking about other stuff, but let's back up and talk about this graph that I said, hey, what do you think? So, in the slide directly following this, I was showing the generation of ocean crust happens at a mid-ocean ridge, and subduction happens on some coastlines. We call this, of course, plate tectonics. Earth has it. Mars does not. The Moon does not. Venus does not. Maybe they did at one time, maybe not. Like the Moon, we do not believe had plate tectonics. Mars probably did, at least briefly. Plate tectonics creates mountains. We get those volcanic arches forming. Those are mountains. We get other kinds of mountains forming, like the Himalayan mountains. We'll discuss later in this lecture exactly how those formed, but we get mountains. And we get those trenches. So, on this slide we see volcanoes, those are mountains. We see mountains over here. We see trenches. We see these highs and these lows. That's these two peaks. If we didn't have plate tectonics, erosion would be the king. Erosion would wear down those mountains, so it would basically erase this top peak here, and all of this, and all that sediment would slump down to the low areas. It would fill in all of this stuff, and everything would end up pretty close to average. Like on Venus. We know Venus hasn't had plate tectonics either ever or for a very, very, very long time. Erosion has completely taken over and gotten rid of almost everything. The only events that still cause high points and low points on Venus are things like meteorite and comet strikes. You slam a 10-kilometer asteroid into a planet, and it's going to cause disruption. It's going to make a big hole, a big low point, and all that material is going to fly up and mound up and create mountains or high points. Not necessarily as large as the Himalayan mountain range, but it's going to create high points. And it'll take time for erosion to wear those down and fill the hole back in, and it won't be perfect. So there is some topography on Venus, despite the lack of plate tectonics, but the vast majority of the land is pretty average, pretty flat. Earth has this bimodal system because we have plate tectonics going on currently, which again we can see the different things going on here. So in the ocean, sure, this is a cross section of the ocean crust, and it is about 6 to 10 kilometers thick in almost all places except right at the mid-ocean ridges. Those are much, much thinner. But everywhere else, it's basically between 6 and 10 kilometers thick. So, bathymetric provinces, what does that mean? Well, it's seafloor relief. It's not a topographic map, it's a bathymetric map. Think of like figuring out what the surface of the bottom of your bathtub would be like, to help you remember bathymetric. There are four primary regions of the ocean floor. There are the abyssal plains, the mid-ocean ridges, the oceanic trenches, and submarine plateaus. The four of these combined in different places add up to give us our bathymetric surface of the bottom of the ocean. So abyssal plains, they average 3 to 5 kilometers deep. So there's a lot of deep water there. 3 to 5 kilometers. And the surface is pretty darn flat. I mean, there's some topography sometimes, but overall it's really flat because everything has been covered with pelagic sediment. Pelagic sediment simply means it's a mixture of shells and dead stuff and clay. So clay is the only sediment size that can wash that far out into the ocean. Because it's so fine, it can stay suspended for a long time. And then everything from, birds dropping stuff as they fly over to diatoms that are floating in the ocean and dying and sinking, and their little shells get added, and shrimp and different things. When they die, it sinks and it becomes part of this pelagic sediment. And it can be pretty darn thick, and it covers up everything and just gives it a smooth surface. So you can see here the abyssal plain, right around that white text, looks pretty smooth. The mid-ocean ridges, these brown, kind of thick-looking lines, there's a ridge in the center, and then lots of little lines sloping away from them, are divergent plate boundaries. These ridges are only 2 to 3 kilometers deep, so they're shallower. They are, after all, ridges. They rise up above those abyssal plains. Pretty tall, really. And they're where the Earth's crust is being ripped apart. And basically, the mantle is bleeding out into the ocean water where it quickly solidifies and creates new crust. So this is where we're growing new crust, so to speak. Now, fortunately, we also destroy crust somewhere, otherwise the Earth would be growing, and that doesn't really work very well with the whole conservation of mass. You can't grow your planet just by having plate tectonics. Oceanic trenches are right along where we do that destroying of crust. The trenches are generally between 6 and 11 kilometers deep, so very deep, and they usually border active volcanic arcs, and they definitely border a convergent plate boundary. So the plates are coming together, one is going down, gives us a trench. Submarine plateaus. This is the fourth bathymetric province, and this is a weird flat area that's shallow. So it's a plateau under the ocean. It's very possible that many of these are from mantle hotspots, which we'll talk about in more detail later. But basically, something that's causing a rising of the surface or a bunch of lava flows that then cool and result in a plateau. But, something that caused the surface to rise up and be much shallower than the abyssal plains around it.